2007, no one was looking for fast radio bursts. Radio astronomers were doing what they had always done, recording vast amounts of data from the sky, searching for known pulsars, mapping background noise, filtering interference from Earth. Then a strange signal appeared. It lasted only a few milliseconds, far too short to be interesting. At first glance, it looked like a glitch, a burst of static, something to discard. But it was unusually strong. When researchers examined the data more carefully, they realized the signal had traveled through enormous amounts of intergalactic matter. Its radio waves were stretched and delayed in a way that only happens across cosmic distances. This wasn't interference from Earth. It wasn't from the Sun. It wasn't even from our galaxy. That single millisecond burst had come from billions of light years away. The energy released in that moment was staggering, equivalent to what the Sun produces in days or even weeks, compressed into a blink of time. And then it was gone. No repetition, no warning, no known source. At the time, astronomers didn't even know what to call it. The signal sat in archives for years unnoticed, dismissed as a one-off anomaly. But it wasn't alone. As radio surveys expanded and archives were rechecked, more bursts appeared. Different telescopes, different parts of the sky, same impossible characteristics. Something in the universe was producing ultra-powerful radio flashes, briefly, unpredictably, and at enormous distances. And humanity had almost missed them entirely. Radio astronomy is messy. The universe is full of noise. Pulsars pulse. Quasars roar. Galaxies emit a constant radio hum. On top of that, Earth adds its own chaos. Satellites, aircraft, phones, radar. Most of what radio telescopes record is filtered out. Fast radio bursts didn't fit any known category. They were far brighter than pulsars, far shorter than quasars. And unlike repeating signals, most appeared once and never again. To confirm they were real, astronomers needed one thing above all: repetition across instruments. As new radio telescopes came online and old data was reanalyzed, detections increased. Different observatories, different teams, same signature. The dispersion pattern, the way lower frequencies arrived later than higher ones, acted like a fingerprint. It showed the signal had passed through intergalactic plasma. These bursts were not local. They were cosmological. Once that was clear, skepticism faded. The question was no longer, is this real? It became, what on Earth or not on Earth could do this? The problem was scale. To generate such power in such a short time, the source had to be extreme. That's violent, compact. Whatever was producing fast radio bursts was not gentle, and it was happening across the universe. For years, fast radio bursts were ghosts. Astronomers could detect them, but not locate them precisely. Single-dish radio telescopes see large patches of sky. When a burst arrived, its exact origin remained uncertain. That changed with interferometry. By linking multiple radio telescopes across vast distances, scientists created virtual telescopes the size of Earth. This allowed precise localization, down to individual galaxies. When the first FRB was traced back to a host galaxy, the result was surprising. It didn't come from a galactic center. It didn't come from a black hole. It came from a normal-looking galaxy. Later localizations revealed diversity: dwarf galaxies, spiral galaxies, star-forming regions. Fast radio bursts were not tied to one type of environment, but there was a pattern emerging. Many seemed connected to regions rich in young, massive stars, places where extreme stellar remnants could form. The mystery was narrowing. We didn't know what was producing the signals yet, but we were finally learning where to look. And that was only possible because humanity learned how to coordinate instruments across the planet, timing signals down to nanoseconds, sharing data globally, and combining perspectives. No single telescope solved the mystery. A network did. Then came the breakthrough no one expected. One fast radio burst repeated. Again, and again, and again. This shattered early theories that FRBs were caused by one-time catastrophic events like star explosions. Whatever produced this signal survived. Repeated bursts allowed continuous monitoring. Patterns could be studied, frequencies compared, environments analyzed, and slowly, evidence began pointing toward one of the most extreme objects in the universe. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. Magnetars are unstable. Their crusts crack. Their magnetic fields snap and realign. When they do, they release enormous energy. In 2020, humanity observed something unprecedented. A magnetar inside our own galaxy produced a radio burst, weaker than extragalactic FRBs, but with the same structure. For the first time, there was a direct link. Fast radio bursts were no longer completely unknown. They were extreme, but physical. And they were detectable only because humans had learned how to listen carefully enough. Unlike optical astronomy, radio astronomy does not rely on images. It relies on listening. Radio telescopes do not see stars or galaxies. They collect faint electromagnetic waves, whispers emitted by distant objects, and convert them into data. For decades, these instruments were built to study known sources: pulsars, quasars, cosmic background radiation. They scan the sky slowly, recording steady signals. Fast radio bursts changed the rules. They were too short, too rare, too unpredictable. A telescope could scan the same region for years and miss them entirely. To catch something that lasts milliseconds, humanity needed coverage, not precision at first, but presence. That meant building wide-field radio telescopes capable of monitoring huge portions of the sky continuously. Facilities like large dish antennas and distributed arrays became crucial. Instead of focusing on one small target, astronomers began listening to everything at once. This was a shift in mindset. The universe was no longer something to point at. It was something to monitor. And the Earth itself, spread with instruments across continents, became a single listening platform. The breakthrough came when astronomers stopped chasing signals and started waiting for them. New instruments were designed to do one thing extremely well: never stop listening. Instead of moving parts, some radio telescopes used fixed designs, relying on Earth's rotation to scan the sky. This allowed constant, uninterrupted monitoring of large sky regions. One such system transformed FRB research almost overnight. By watching the sky continuously, these telescopes began detecting fast radio bursts regularly, sometimes several per day. For the first time, FRBs were no longer rare anomalies. They were a population. This flood of detections allowed scientists to compare bursts statistically. Durations, frequencies, dispersion patterns, all could be studied in bulk. Patterns emerged. Some bursts repeated. Some did not. Some showed complex frequency structures. And crucially, detections were no longer dependent on luck. They were the result of engineering decisions. Humanity didn't wait for the universe to cooperate. It built instruments that forced the universe to reveal itself. Detection was only half the problem. Localization was the real challenge. A single radio dish can detect a burst, but it cannot say exactly where it came from. The sky area is simply too large. To pinpoint a millisecond signal, astronomers needed timing precision beyond human intuition. They achieved this by linking telescopes together using interferometry. When multiple telescopes detect the same signal at slightly different times, those delays can be used to triangulate its origin. The farther apart the telescopes, the better the resolution. By synchronizing observatories across continents using atomic clocks, humanity created virtual telescopes the size of Earth. This allowed localization of FRBs to specific galaxies, sometimes even to specific regions within them. What was once a flash with no address became an event with coordinates. And that changed everything. Now astronomers could study host galaxies, star formation rates, magnetic environments. They could connect signals to physical conditions. Listening had turned into mapping. Fast radio bursts didn't challenge humanity's imagination. They challenged its data systems. Each radio telescope generates enormous data streams, far more than humans can examine manually. Early FRBs were found by accident because automated systems were not designed to flag such brief events. That had to change. New pipelines were developed to process data in real time. Algorithms filtered noise, identified dispersion patterns, and flagged candidates instantly. Machine learning began playing a role, trained to recognize the signature of real cosmic bursts and reject interference. This was not glamorous work. No launch, no spacecraft, no dramatic images. But without it, fast radio bursts would still be buried in archives. Humanity didn't just build ears to listen. It built brains to understand what it heard. And that combination, instruments plus interpretation, turned fleeting signals into one of the most active fields in modern astronomy. One of the first assumptions about fast radio bursts was simple. There must be one cause, one type of object, one extreme event, one explanation that fits all. That assumption did not survive the data. As more FRBs were localized to their host galaxies, astronomers noticed something unexpected: diversity. Some bursts came from small dwarf galaxies rich in star formation. Others came from large spiral galaxies not unlike our own Milky Way. Some originated in dense stellar neighborhoods. Others came from quieter regions. Fast radio bursts were not confined to a single cosmic environment. This forced a major shift in thinking. Instead of asking what causes FRBs, astronomers began asking what kinds of objects are capable of producing them. The answer appeared to be more than one. Some FRBs repeat. Some do not. Some show complex frequency patterns. Others are clean, single spikes. The evidence suggested a family of sources, not a single mechanism. But within that family, one candidate stood out as capable of explaining many, though not all, observed properties. An object extreme enough to release enormous energy, compact enough to do so in milliseconds, and common enough to exist across the universe. The strongest candidate to explain many fast radio bursts is the magnetar. Magnetars are neutron stars, the collapsed cores of massive stars, but with a critical difference. Their magnetic fields are among the strongest known in the universe. These fields are so intense that they stress the star's solid crust. When that crust fractures, enormous amounts of energy are released. In 2020, something remarkable happened. Astronomers detected a powerful radio burst from a magnetar located inside our own galaxy. The burst was weaker than extragalactic FRBs, but its structure was nearly identical. For the first time, a known object produced a signal that looked like a fast radio burst. This did not solve the mystery completely. Not all FRBs can be explained by magnetars alone. Some bursts are too energetic. Others occur in environments where magnetars should be rare. But the discovery did something crucial. It proved that nature can produce FRB-like signals using known physics. What once seemed impossible now had a working model. Humanity did not guess this connection. It observed it by listening carefully long enough and across enough of the sky. Fast radio bursts turned out to be useful in an unexpected way. They are not just phenomena to explain. They are tools. As FRB signals travel across billions of light years, they pass through clouds of ionized gas between galaxies. This gas slightly delays lower frequency radio waves more than higher ones. By measuring this delay, known as dispersion, astronomers can estimate how much matter the signal passed through. This allowed scientists to do something that had been difficult for decades: map the missing matter of the universe. Astronomers had long known that a large fraction of normal matter was unaccounted for. It wasn't in stars. It wasn't in galaxies. FRBs revealed where it was hiding, spread thinly through intergalactic space. Each burst became a probe, sampling the universe along a single line of sight. With enough bursts, a three-dimensional picture of otherwise invisible matter began to emerge. Fast radio bursts were no longer just mysterious flashes. They were measurement instruments, created by the universe itself. And humanity learned how to use them. After more than a decade of study, fast radio bursts are no longer invisible. But they are not fully understood. Astronomers now know. They are real. They are extragalactic. At least some come from magnetars. They can be used to study the structure of the universe. But major questions remain. Why do some FRBs repeat while others do not? Why do some show complex frequency patterns? Are there multiple mechanisms producing similar signals? Answering these questions will require even more sensitive instruments. New radio arrays, wider surveys, faster data pipelines. Humanity is still listening. And this time it knows what to listen for. Fast radio bursts began as millisecond anomalies almost erased from data logs. They became one of the clearest examples of how progress in astronomy works. Not through a single discovery, but through patience, engineering, collaboration, and the ability to recognize that a signal matters, even when it appears only once. The universe spoke briefly. Humanity learned how to hear it.